So we're going to kick off, and it's a great pleasure to introduce David Power from CrystalMaker, who is behind the software, developed it, markets it, runs these courses for us, etc. And so David has spent many years developing the CrystalMaker software to explore crystal structures and visualization of crystal structures, as well as looking at their diffraction data and so on and so forth. And the CrystalMaker package I found as a particularly useful tool for us in our research. It's something that we do have a departmental license for, so you will all be able to access CrystalMaker and download it, have it on your own machines with the departmental license codes. So if you find the tools that Dave is going to describe this morning to be of use to you, let us know, and we'll make sure that those codes for the CrystalMaker package and the suite of packages, because it's not just the visualization, we have the single crystal and so on as well. So there's a whole suite that we can make available to you to assist with your research. So I'm not going to say any more, and I'm going to hand straight across to David to take you through this. We've got a session of about an hour of an introduction, I believe, just to take you through what CrystalMaker packages can do. And then we'll have a bit of a break, and then there's a sort of hands-on-y type workshop problem-solving session. There's some questions already being submitted to David, so we can have a little bit more of an interactive session at that stage to take you through some of the power of the software. So David, thank you very much for doing this once again this year. It's very much appreciated by the CDT, and I'll hand over to you and let you take the session from here.
Okay, well, thanks very much, Stephen, and thank you to everyone who's come along. I should just start off by saying that I'm not exactly a Microsoft Teams expert, so if you see me fumbling slightly, that'll be why. But what I'm going to do is start off by trying to give a brief introduction to our software to sort of get you started. And as Stephen said, then there will be a second half where we can do slightly more interesting and interactive things. So let's have a go at sharing my screen. And hopefully you can all now see some flowers, which is my desktop. And I'm just going to bring up a little presentation. Let's see if that's working. Okay, so seeing the wood for the trees, that's really the raison d'etre behind what we do at CrystalMaker software. And the reason that we developed the software, and I say we're a small company, we have 4 or 5 employees based here in Oxford, but it started off just me as an academic having to teach crystallography as part of a materials-y type course. And there were 2 big issues. Visualization of 3D is always a challenge. The other challenge, of course, is that structures can be very complex. And sometimes it's difficult to get your eye in and understand complexity. Complexity is a fundamental problem with science. And there are ways in which we can deal with complexity in terms of thinking about fundamental building blocks and maybe simplifying those. And that's what I regard as being a bit like the Lego model of crystallography, crystal structures, material structures. If you can understand the fundamental Lego brick, then you can understand the way in which the bricks pack together, and then you can understand the structures and their properties. And we wanted to develop software that would allow you to do that. So we provide some software packages as part of the site license, and the main package is CrystalMaker. And we also have 2 diffraction programs that work with CrystalMaker to simulate powder diffraction, that's Crystal Diffract, and single crystal diffraction patterns, single crystal. And we've tried to make the site license very flexible so that individuals are empowered to use the software on their own computers, because that's the best way to learn, and that's the way in which it's going to be the most effective. So just to summarize, we want to be able to help your research. We want you to be able to present your results. And we also want to be able to drive good teaching. We want people to find the software fun. And if you don't find our software accessible and fun, let us know, because it means we need to improve what we're doing and up our game. So the first package we're going to talk about is CrystalMaker, which is our visualization package. And this has been around now since 1994 or the end of 1994. And in fact, our first customer was a materials student in Cambridge, and we developed the software from there. Now, a few years ago, we brought out an all-new version of CrystalMaker, CrystalMaker 10. This is a 64-bit program and had a radical new design. And the idea was to try and make the software more powerful for people who needed to be able to work with structural behavior, phase transitions, and also simulations. So I'm going to start off by showing you the sort of entry point to CrystalMaker, which is the Crystal Structures library. So let's just move CrystalMaker onto the appropriate screen. Now I take it everybody can still see, let me just cancel my desktop for the moment. Everyone's still there. I take it everyone actually saw a bit of a presentation there and not just me. Is that right? Yeah, good, excellent. People are nodding. That's fantastic. I'm going to go back into desktop mode. It's always good to know that one's not talking to oneself and that one's not being a complete and utter fool. So things seem to be working. Excellent. Thank you for that. Well, let's go back and have a look at CrystalMaker then. And actually, I'm going to share the entire screen so we can screen number one. It looks like it. Good, okay. So I've launched CrystalMaker, and the first thing that happens when you launch CrystalMaker is you see a little window, which is our library window. And this is something that you don't have to show. You can set a preference not to show it if you don't want to, but it does allow you access to a library of structures, and it provides a way in which you can organize your own structures. So the library window is divided into two halves. We have a sidebar, which you can toggle on or off, and a series of what we call collections. So you can find our documentation here. You can look at your recently opened files. You can add favorite structures to the window by dragging and dropping them into there. We provide some examples, and then we have a library of reference structures. And you can drill down through these, so we can have a look at hybrid materials. And we've got clathrates, MOFs, SIFs, and these structures can be opened in the main window by double-clicking. Or you can preview them by clicking on the little info button, and you get a little bit of information, and we can navigate within the window. So we've actually provided a library of about 1,200 structures, which is organized by folder. You can use the toolbar to view every single structure, or you can view it by folders, and we have a search command if you want to find a particular material. Now, why is this useful? You've all got access, presumably, to online databases. The reason is we've tried to provide some carefully curated structures, and we have a search command. So let's say we want to find barium titanate. I can type in the formula BaTiO3. We have the phases that contain barium, titanium, and oxygen. You'll see there's a little search bar that appears along here, and I can customize my search. I can search by formula. I can search by structures whose elements are in there. So we find everything that contains barium and oxygen, for example. We have more structures and so on. Or you can search by name. So let's have everything that contains perovskite. So we've got a folder of perovskites, and then we have some phases that actually have perovskite in the file there. So you get the idea that this is a searchable library that might be useful. There's some teaching collections and some thematic collections that are there for fun as well. So that's really the entry point into CrystalMaker. As I said before, you can take any of these structures and you can double click them to open in the main program. Some of the structures have little animated thumbnails. If you move the mouse over the thumbnail, you'll see the thumbnail animates. If you double click that in CrystalMaker, then you'll see that we've actually provided a series of structures saved in the same document. Okay, so that was our structures library. So just to summarize then, this provides a springboard to open structures. It also provides links for documentations, for favorite files, for browsing examples. It's a reference library, and you can explore using an integrated Crystal viewer. Now let's talk about the actual document interface in CrystalMaker. This is something that you'll be using all the time, and many of you may already be familiar with it, but I'll go through it anyway because it underlines the sort of architecture of the program. Oops. Okay, let's go back. Okay, here's the typical CrystalMaker document window. And this is divided up into standard parts. Here's a toolbar. Unlike other programs, we have made our toolbar customizable. You can right-click in the toolbar and show or hide which buttons you find useful. You'll get the main functionality in the menu bar, so you don't have to have everything visible in the toolbar if you don't want to. On the left-hand side, you may or may not see a slide-out structures list. Now, this is important because we've made the program multi-structure. Not only can you open multiple document windows, but each window can contain more than one structure. And this allows you to do things like visualize how structures change with pressure or temperature. You can look at frames from simulations, and you can also readily compare structures in the same window. So each structure is listed with a thumbnail, and you can click on the thumbnail to show that particular structure. Now, in the middle of the window, of course, we've got the meat of the software, which is our graphics pane, and there's a little ruler at the top to give you an idea of scale. The scale is in angstrom units, and we like angstrom units here at CrystalMaker Software because an atom is about an angstrom in radius, so it's a good, useful size. I always feel that nanometers are about a factor of 10 too big. And then at the bottom, you'll see a little tool strip. Now that may disappear if you move the mouse outside the window, and that provides tools for rotating and manipulating your structure. You can also display a little information log. You can hide that. That shows the results of bond and distance searches. And on the right-hand side, we have an inspector. And that's really a very powerful part of the program. It allows you to do lots of interactive work on the structure. And here we're showing the info pane, but there are other panes that you can access by clicking on the little tab bar. And that allows you to do things like change colors of atoms, the radii of bonds, and so on. So we've tried to provide you with tools at your fingertips, but you don't have to see all those tools all the time. And this is maybe an important distinction between our software and maybe other software you may be familiar with. We are trying to keep out of your hair, so to speak. As tools are there if you need them, but we don't really want them to clutter up your screen. And one of the ways in which we can hide clutter is by use of these little popover windows, which will appear. For example, if you click on an atom style in the Atoms Inspector, it allows you to change styles very quickly, and then the popover will disappear. Again, it's all about trying to have an intelligent interface that is adaptive, but doesn't get in the way. Some of the panes split in two, and here we can see everything all together. So we're looking at volumetric visualization, and on the right-hand side, we have an inspector that shows some lattice planes, and there's a volumetric data set in the bottom right. And then we've got a series of different views on the left. You can switch into full screen mode, which will hide all the clutter. And we have spring-loaded sidebars, which means if you move the mouse to the left or to the right of the screen, then the inspector will slide into view, or the structures list will slide into view. And then if you move the mouse out, it'll disappear. Again, if you're working on a small laptop, for example, it means you can maximize your screen space without the tools getting in the way. So just a quick summary of what we've seen in a document interface then. Multi-structure by design, customizable. You have a graphics pane to work with, and then there are some sidebars to provide additional content. Okay, now CrystalMaker is more than just visualization. One of the things that we've done with this version of the software is to allow you to be able to build crystals and molecules interactively. And I'm going to now have a very quick example of how to build a molecular structure using CrystalMaker. So what I'm going to do, I'm going to go back to our library window, and there's a little new document icon there. Or we could go to the menu bar and do File, New Window. And now we've got an empty document window, and I want to build a little organic molecule. Now, when you move the mouse into the document window, you'll see a little tool strip appear at the bottom. And one of the tools in that is the Add Atom tool. Some of these tools have little drop-down icons, little V shapes. When you click those, that means that there's a little pop-up. So I have a little palette of atoms here, and I'm going to build an organic molecule by clicking with the mouse. Now, unfortunately, we've got a black background. Black carbon atoms are a bit hard to see, so I'm going to change the background color in a moment. I'm going to click with the mouse to add a carbon atom. You can just about see where I added it. Let me quickly change the background color. I'm going to use the inspector here. And let's change the background color to blue. And let's hide the inspector by clicking the button in the tools palette. And I'll make the window a bit bigger so it fills the screen. Okay, now I'm going to add a second carbon atom. I'm going to build some sort of acid, a simple structure. And I'm going to add some bonds by holding the Shift key down. So I'm holding the Shift key down, and I'm going to click, 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 click. And let's add some more, so another methyl group here. And then I'm going to add some oxygen. So I'll choose oxygen from the palette. Click on this carbon atom to select it again. I'm going to shift click to add another oxygen. Let's add a hydrogen. And I'm going to add a few more here. Now this looks incredibly crude. This is the sort of thing that a 2-year-old might draw. Okay, there we are. There's our organic molecule. That's very crude. Fortunately, we have some tools to help us out here. So if we go up to the toolbar, there is a relax command. If we click that, then the program does an energy minimization calculation. And we now have a nice, relaxed organic molecule. Now I'm going to just tidy this up a little bit. We've got some black carbon atoms, and we've got some hydrogen atoms, and we've got some oxygen atoms. Where do these colors come from, and where do these sizes come from? At the moment, we're at the creation stage, and we've done some magic. If we go to the second pane in the inspector, you'll see we've got a list of atoms, and we've got the colors. We've got carbon. I can toggle that on and off using the visibility button. I've got hydrogen, and I've got oxygen. Where did those colors come from, and where did these radii come in? You see the radii is given in this column here, radius in angstroms, 0.29 angstroms for carbon, 0.1 for hydrogen, and 1.2 angstroms for oxygen. Well, the answer is that we have all this stuff tabulated, and this illustrates a very interesting point. The size of an atom depends on the type of bonding. And if you regularly work with ionic structures, then you're going to come across a different set of radii compared to somebody who regularly works with organic structures. And most of the time, this is fine because in chemistry, you tend to have inorganic chemists and organic chemists. But you're in materials and you're at the cutting edge of technology. So you're dealing with hybrid materials and all kinds of interesting things. So you're going to have to think a little bit about bonding. Now, if we go to the preferences command, now, depending on whether you're using Mac or Windows, it's either under the Edit menu or the CrystalMaker menu. We can open up a little Preferences window, and there is an Elements tab. And here we see a periodic table of the elements. You can view that in List View or in Table View. And we can switch between different sets of radii. So if you regularly work with inorganic structures, we recommend that you use the CrystalMaker or the Shannon and Pruitt ionic radii. If you regularly work with covalent structures, then you probably want to use covalent radii. And you'll notice I've just selected that my atoms got bigger, and carbon in particular is 0.76 angstroms. That's the covalent radius of carbon. So let's go to our organic molecule here, and let's change the radii so that they are organic radii. Now I could edit this directly. I could put something stupid in like 1.5, but we want to use our tabulated radii. So we're going to use this actions menu in the top right-hand corner, and we'll go down to radii, and we'll use one of the presets, SAR covalent radii. SAR stands for one of our CrystalMaker users, Santiago Alvarez, who's a professor of inorganic chemistry in University of Barcelona, and he's actually published a set of definitive radii. So now we've got some nice radii, and I'm going to change the color of my carbon to brown. And the other thing we might want to do now that we're happy with our radii, maybe we can label the atoms by clicking on some labels. We've generated some bonds automatically. We could label those. But I think what we'll do next is we'll maybe change some of the bonds. So far I've been working with this hand tool. I can click and drag to rotate. I want to maybe show some double bonds in the structure. So I'm going to go down to the tool strip, and I'm going to select the arrow tool, and I'm going to make this carbon-oxygen bond a double bond. Now, this is purely visual. The program doesn't care what type of bond it is. It's purely visual. I'm going to select this. Whenever you make a selection, CrystalMaker, that selection can be shown in this far right tab of the inspector, the selection inspector, and we can change things to the selected objects. We can change the colors and the styles. Let's change that to a double bond, and let's do the same for some of these bonds here. So I'm going to hold the shift key down to extend my selection, and I've now got some double bonds. There we are. Now, you may have noticed that if you use the arrow tool and you hover over a bond, you get the distance shown. If you hover over an atom, you get the atom and its bonds highlighted. If we select that atom, then the selection inspector will show us the little tabulation of the distances around that atom, and we can get some more information using the atom properties as well. Okay, let's say we want to measure angles. We can go down to the tool strip and we can use the angle tool. And again, you can hover over gaps between atoms to see the included angles. You can also click on groups of atoms. And we can interactively see the bond angle. If you want to fix the measurement, click again a third time, and we now have our measurement is fixed. We can rotate the structure and we can see that bond angle 89.7 degrees. If you want to record that measurement, then we can display an output log by clicking the little output button, and this is the output, bottom of the screen. There's our bond angle, 89.74 degrees. Let's just close that. Now we can measure other sorts of angles. We can measure torsion angles. That's the angle between four atoms. In our case, it's 0 because it's a planar molecule. And we can also measure angles in the plane of the screen, so not just between clicked atoms. So again, I'm using these little pop-up indicators to show some menus that give us a bit more content. We have a bond distance tool, again, that allows us to interactively measure distances between atoms. Again, we can click to fix the measurement, and the output will be shown in the output pane. We also get the bond vector between the two clicked atoms. So that could be useful. Okay, that was a simple organic molecule. We've seen how we can change radii, we can change colors, we can change bond styles, and we can do some basic measurements. As a bit of fun, we have some energy modeling built into the program. So we were able to relax the molecule, and we can use that energy modeling to tell you something about the vibrational properties of the molecule. So if we go up to our toolbar, then we've seen the relax button. There's also a vibrate button. And if you click that, then we have an instant infrared spectrum for this molecule. Now, if you're a chemist, then you're probably used to seeing your spectrum upside down like this. If you're a physicist, you're probably used to seeing it this way up. This is a simulated infrared spectrum. We can double click any of the peaks to see the corresponding vibrational modes of the molecule. So high frequency modes tend to be the OH stretch, and the very low frequency modes, like down here, tend to be very complicated modes involving torsions. On the left-hand side of the screen, you can see all of the vibrational modes listed. You can select them and actually visualize them. So that's quite fun. I don't know how many of you are working on organic molecules, but if you were, then this is something that you could do. Now, you can also relax more complex structures. Unfortunately, we can't relax crystal structures currently, but the next version of CrystalMaker, which Imperial should get at some point in the next, who knows, the next year or two, will have energy modeling for crystal structures as well. Okay, let's just summarize what we've done. We've used the Add Atom tool to add some atoms and some bonds. We've applied a set of covalent radii using an actions menu in the Atoms inspector. We've had a look at our preferences where we can set our preferred radii for new structures. We've changed some colors. We've looked at some energy modeling. We've selected an atom. We've changed a bond style. We've simulated an infrared spectrum, and we've looked at we've actually visualized the vibrations. I expect most of you are probably working with crystal structures rather than molecules. So we're now going to step up to a more complicated structure. And what you can see here is the way in which crystal structures used to be taught at dusty universities in the dusty past. And that's probably why materials science is quite a recent science, because people used to get really bored, both by the complexity and the 3 dimensions. And what we want to be able to do is to make sure that you can see the wood for the trees and not get lost in the woods. So let's have a go at building a new crystal structure. So let's close this molecule. I think we've finished with the molecule now. Let's build a new crystal structure from scratch. Now, most of the time you won't be doing this. You're going to be opening a crystal structure, probably saved as a CIF file or an XYZ file or one of the other file formats. But I think it's useful to go through the motions of building a crystal from scratch, because at some point you may need to edit a crystal. You may need to build your own from data in the literature, but it also shows you the kinds of steps that you can go to produce a very nice visualization. Because ultimately what you're doing is both improving your own visual understanding, but also communicating with other scientists. So let's have a go at building a new crystal structure. Now, we could do this by pointing and clicking with the mouse, but with crystals, there's symmetry as well, and that complicates things. So we're going to build a crystal using the crystal editor sheet. So when we build a new crystal, then we are presented with a dialog if you're using Windows, or a sheet if you're using the Mac, and that asks you to build your crystal in terms of 3 fundamental sets of parameters. We need to know something about the symmetry of the crystal. We need to know the size and shape of the unit cell. That's the fundamental building brick of the crystal that's going to be repeated ad infinitum in 3 dimensions. And then we need to know what's actually inside the building brick. We're going to use the atoms inside the building brick in combination with the symmetry to produce an extended structure. So let's get cracking. I'm going to build the structure of spinel. And spinel is a cubic material. And so I'm being prompted to enter a space group. And that's a very fancy name for a collection of 3D symmetry elements. And space groups have got funny titles. And you can use the browse button where you can just type in. So I can do FDR3M. That's my space group. If you're a little unsure about space groups, you can click the browse button and you'll see that we have a listing of crystal systems and lattice types for each crystal system, and then the space group symbols for the particular lattice type. We can also show unconventional settings, which is what we're going to need to use here. And it turns out, actually, I need an unconventional setting, FD-bar3M. I need origin choice 2. Now, the program has now recognized that I've entered a cubic space group, and so therefore I only need to specify one side of a cube. By the way, if you want a bit of fun, you can click on the Explore Symmetry button, and that shows you how that collection of symmetry elements will operate on a single unit. And you can have some fun playing around with this. So we can put in something like P1, and you've just got one atom in the unit cell, and then we can go for something like IA-R3D, and we've got more, and we can really play around with this. You can play around with the positions of these atoms and see how the symmetry goes. Quite useful for teaching, maybe not so for research. So let's stop messing about. Let's go back to FD-bar3M origin 2. My cell parameter is 8.08 angstroms, and I've got 3 atoms I need to enter. So the first atom I'm going to enter is aluminium. Now, each atom needs some coordinates, which are going to be fractions of the cell parameter. We need to tell the program what sort of atom it is, and we need a label. It's always useful to label atoms. So I'm going to call this M, and I'm going to define the occupancy, what type of atom it is. I want aluminium. Now, you can actually define mixed occupancies. Many interesting structures have disordered arrangements, say, of aluminium and silicon. So I might put in something like aluminium 0.5, silicon 0.5. Could do that if I wanted to, but I'll make this pure aluminium. And this atom is at a half, a half, a half. So I can just type fractions, 1/2. I can type decimals. These things on the right-hand side, don't worry about that. U11, U22. These are the thermal parameters. Most of the time, you'll just read those in from a data file. I've also got magnesium in here. I'm going to call my magnesium site T for reasons that you will soon discover. So magnesium, I'm pressing the tab key to move between fields. Sorry, this is probably really boring at the moment, but we're getting there, don't worry, bear with me. So 1/8, 1/8, 1/8, and we need some oxygen. Call that O, and that's at 0.262, 0.262, 0.262. Okay, so I've basically got 5 sets of data: space group, cell parameter, and then 3 sets of coordinates. The program now, when I press this little OK button, is going to do some magic. It's going to take all of those coordinates and combine them with symmetry to give me positions of atoms in one unit cell. And the unit cell is shown by the white lines. There we go. Now, normally when you read in data from a file, the program will actually generate bonding automatically as well. But we're doing this from first principles, so we're doing things the hard way. Now, I'm going to go to the atoms inspector. Well, actually, before I do that, we're in the info inspector here. The info inspector allows you to type some notes. So that's the crystal structure of spinel, and we can have subscripts and things. So MgAl2O4. select something and turn that into a subscript. And you'll notice at the bottom, we have a little overview pane, which gives us some data on this. It gives us the density of the structure, how many atoms are in the unit cell, and so on. And it even gives us a list of the basic unit, what we call the asymmetric unit. That is the minimum group of atoms, which when combined with the space group symmetry, is able to give us the full contents of one unit cell. I'm sure this is all obvious to all of you, but anyway, there we go. Let's go to the Atoms Inspector. And the first thing I need to do is I changed our radii to covalent radii. I'm going to go back and I'm going to switch to the Shannon-Pruitt ionic radii. And I'm going to change the colors to one of our presets. I'm going to use the CrystalMaker colors because I'm familiar with those. There we go. Let's just double check our structure. Origin 2, R3M. Okay, now we might want to define some bonds between atoms. Now, if we go to the Nets Inspector along, the bonding inspector, we can add bonds by just double-clicking and defining an element pair. So let's say we want bonds between aluminium and oxygen. Then the program will try and figure out a sensible maximum distance for bonds based on the sum of the radii. This is why it's important to get the radii right. And there's a general rule of thumb that if two atoms are within about 15% of the sum of their radii, then there's likely to be a chemical bond between them. I could do the same again for magnesium to oxygen. And there we've got our magnesium oxygen bonds. Or I can select both of these rows, delete that, and I can go up to here and I can do auto-generate bonds. And the same thing will happen. Now, the auto-generation of bonds has also given us oxygen-oxygen bonds. We don't want that, so let's select that row and hit delete just to hide that. Now, this isn't a very nice model because the atoms at the edge are a bit lonely. They don't have any friends. So we need to show a few more atoms to get a decent looking plot. And CrystalMaker, of course, can generate as many atoms as you like. And the way that you do that is by extending the range of atoms in 3D space. We're going to be transforming this model by adding more atoms, and all of the operations you need are on the transform menu. So if you go down the menu, we go to atom range, and there is a set range command, which has a keyboard shortcut. It's Control R on Windows and Command R on the Mac. Now there's a shortcut to get there on the toolbar, and you'll see there is a range button. So if we click that, we get a little pop-up, a pop-over window, and we can use this window to expand the range of atoms in all directions. Now, at this stage, I should note that all of our little popovers can be detached from the toolbar, and you can leave them open while you work if you need to use them again. Now, you'll see that the range of atoms along X, Y, and Z is 0 to 1. This is fractions of the unit cell. So we've got one complete unit cell here. We can change those fractions individually, or we can use the buttons at the bottom to do a little bit more. I find it very useful to click on the expand range button. That expands the range by 10% in each direction. So we can expand a little bit more and a little bit more. And now we've got a bit more of a structure. And now you can see that, at least I hope you can see that our aluminium atoms have got 6 atoms around them, 6 oxygens around them, and the magnesium atoms have got 4 atoms. It turns out magnesium's in tetrahedral coordination, but we're going to look at that in a bit more detail now. Now we can rotate this using the mouse. CrystalMaker allows you to use the hand tool, so you can click and drag to rotate. If you want to rotate about an axis coming out of the screen, hold down the Shift key and then rotate in a clockwise or anti-clockwise direction. But most people these days have trackpads, and CrystalMaker supports multi-touch. You might even have a Windows computer with a touch-sensitive screen, in which case you can just use touch gestures to move across the screen. So I'm just rotating this now by moving some fingers across my trackpad, and I can use a rotate gesture or a swipe gesture to rotate about different axes. What happens if you want to be a bit more precise with the orientation of the structure? Well, again, we can use the transform menu to set the view direction. And the shortcut here is to use this orient button. And I'm going to look down the 111 direction. In fact, there's a shortcut here. There we go. And if you want to rotate precisely, we can use a little rotator. Let's drag this off. And you can type an angle into this field or use the pop-up. We've got 90 degrees as our default, and I'm going to flip this to 90 degrees so I can see the structure sideways on. Now, one of the fun things about CrystalMaker is that we can make complicated structures easier to work with. So let's use the arrow tool, and let's isolate 2 layers of oxygen atoms. And I don't know if you can see on your screens, but I've clicked and dragged to define a rectangle. I'm going to let go of the mouse and all those atoms are highlighted. I've got some information shown in the selection inspector on the right, but I want to isolate my selection. Now, I can do that by going to the transform menu, transform selection, isolate, but a convenient shortcut is to right click and do isolate selection. Now I'm going to take the upper layer of oxygens now and draw a rectangle around those. They're selected. I'm going to use the selection inspector to change the color of those atoms to green. And let's switch now from this rather boring ball and stick model to a space filling model so we can see the correct relative sizes of the atoms. We'll go to the model menu and we'll choose space filling. And you can see that the oxygen atoms are quite a bit bigger than the metal ions. Let's hide the unit cell. Let's use the rotator to flip through 90 degrees. And now we can see that we've got 2 layers of quasi-close packed oxygen ions, colored red and green, with the metal ions, which are yellow and blue, sitting in between. And let's focus on that. I'm going to select one of these T sites, magnesium, and this blue site, this M site, which is aluminium. And I want to show the coordinations of those atoms. If I right click, I can extend my selection to show the nearest neighbors. And we'll isolate that selection. Now, before I do that, I don't want to lose this view. So I'm going to open up my structures list. And I'm going to right click on the little thumbnail and I'm going to do duplicate. And I'm going to click on the title here and say, let's call this close packed layers. So we've saved a view. Let's go back to the main view now. I can hide the structures list. Let's isolate that selection. Let's switch to a ball and stick view. And let's just have a little rotation. We can hover over the atoms and look at the distances between the atoms. We can measure angles if we need to do that. We know how to do that now. We can use the angle tool. We can just hover over the included angles. We've got a tetrahedral angle here, an octahedral angle here. Let's go one step further, and we'll want to simplify this. We've looked at a space filling model. We've looked at a ball and stick model. Let's go to model, polyhedral. And now we're going to replace those units with solid polyhedra, where the oxygen atoms define the vertices of the polyhedra. That was quite a brutal step. So I'm going to backtrack a little bit. I'm going to go to the atoms inspector. And you'll see now it's showing a blue polyhedron for aluminium and a yellow polyhedron for magnesium. We can click on these icons to get a popover, and that allows us to change the style of the tetrahedron or octahedron. And I'm going to choose a translucent style so I can see the atoms inside. And the oxygens have got a cross. That means that we have a blank style for oxygen. I'm going to choose a sphere style. So we're back to pretty much where we started, a ball and stick model, but we can see these translucent octahedra. These are like putting a fluorescent highlighter through a group of atoms. It shows you the coordination environment. And now you can see why I called the magnesium site T, because it's a tetrahedron. This is a tetrahedral group, and this is an octahedral group, which we conventionally, for some bizarre reason in crystallography, designate M. Now you can customize these styles further. We've chosen translucent octahedra with a ball and stick style. I can customize that more by going to the model inspector. And if we go down to polyhedra, we can change the opacity of our faces. I can change the frame. I can have a dark frame. I can change the thickness of the frame. And I could choose to show thermal ellipsoids at the vertices or spheres. Now, we don't have any temperature data, so we can't show ellipsoids here, but we'll just show the spheres. So there we are. So that's a simplified model. I think once we get used to the idea of polyhedra, we can simplify them further and just have opaque polyhedra. And we can probably hide the oxygens completely. And then we can go back using the range command to show a unit cell and its contents. And now our spinel structure, which is a ball and stick model, is really quite a mess. And as a space filling model, is impenetrable. But as a polyhedral model, we can see that we just got two units. We've got two Lego blocks, and they consist of edge sharing octahedra and vertex sharing tetrahedra. And that's all there is to that. So we've done an awful lot in a very short amount of time. We've used the crystal editor to build a crystal structure from scratch. We've generated bonding, we've toggled sites, we've made a selection, we've isolated selections, we've changed colors, we've saved a view, and we did a little bit of measurement. So that was really the nuts and bolts of how CrystalMaker works. Now, most of the time you won't be doing this. You'll just be taking a file and you'll be importing it into the program. And CrystalMaker can support, we actually can import about 44 different file formats. You can use the open with format menu if you know the file format, but most of the time you actually don't need to use this menu at all. CrystalMaker can figure out the file format simply by the file extension. So let me just open up an example of a CIF file. CIF is the main format used in crystal structures these days. And here we have a calcium manganate structure with a .cif extension. You'll notice it has a CrystalMaker style icon. You can double click this to open it up in CrystalMaker, or you can just use the open command. I'm going to double click, and there is our structure. It's opened up in CrystalMaker. Now, unlike when we built our structure from scratch, CrystalMaker has automatically generated bonds for us. That's actually a preference. If we go to your preferences palette, go to General, under File Import, automatically generate bonds is turned on. Sometimes you may want to turn that off if your structure is complicated, and sometimes you may want to edit the bonding. We don't want manganese bonds, let's delete those. We don't want calcium bonds, let's delete those. But when you import a CIF file or any other file, we try to be very honest with you. I know there are other programs out there that try to be clever, and sometimes you can get into a bit of a mess. So we always show you one unit cell of your material, and then you can use the range command. It's always good actually to expand the range slightly. Let's actually add another unit cell along the z-axis. And let's switch now to a polyhedral model. Let's go back to the inspector, and let's say that we want our calciums to be shown with a ball and stick style, and our manganese can be shown as polyhedra. I think I probably want to delete the calcium manganese bonds, and I'm going to expand the plot range just a little bit more, and we can see we've got some layers. Let's expand a bit more. And now I can see I've got some holes in these layers of manganese. If we go to the atoms inspector and click on this little disclosure triangle, there are actually two manganese sites, Mn1 and Mn2, and I'm going to color them separately. Now I could click on those sites with the arrow tool and change the colors, but that's going to be tedious if you've got a large plot range. So we'll just use the color command here to change every single site. So let's have a light pale site for the Mn2 sites. And there we are. We can see we've got a layered structure. And you notice that some of the calciums actually poke up into these holes, and the other calciums poke down into the lower holes. So that's an example of calcium manganese oxide as loaded from a CIF file into CrystalMaker. Again, you can play around with the styles to your heart's content. We can change the bond styles, we can change the polyhedral styles, and so on. For those of you who work with molecular crystals, the program might seem quite frustrating because by default we show you one unit cell when you first start, and molecules typically extend beyond one unit cell. The program does have some molecular crystal tools, and we have some very helpful commands, one of which is called show molecular cell, which looks for molecules and changes the range automatically so you get an intact range. So if you work with molecular crystals, fear not. We have those commands there. And just a reminder, if you're regularly working with organic structures, use the preferences command to ensure that you have covalent radii. There are all kinds of other commands available to allow you to isolate molecules, to measure distances and angles between molecules. Those commands are there. We don't have time to talk about them now, but they are available. We also have the ability to create dummy sites within complex structures, which allow you to simplify complex frameworks. I'm going to very quickly show that. This is a very helpful tool for those of you working with complex frameworks. Let's have a look at ZIF 11. Okay, here we go. This is a very complex zeolitic imidazolate framework. We try to simplify things a little bit by showing the molecular groups using planes, but there's a little trick that you can use to simplify complicated structures that have cages. And the way it goes is this. You want to hide, let's go to a ball and stick model first of all. That looks horrible. Let's hide everything apart from the important metal ions in the structure. And we're going to isolate part of the structure. Isolate selection, hide the unit cell. Let's just rotate this. I've actually got two large cages here. And I'm going to isolate one cage. Okay, now I'm going to select all of the atoms in view, right click, and I'm going to add a centroid atom. This is a dummy atom that I'm going to put in the middle of my group of atoms. I'm going to give it a dummy element symbol and a site occupancy of 0, so it won't mess up our formula. And the program will add that site with some bonds. Now, what's the point of doing this? It's really to simplify things. You can then switch to a polyhedral model. And this dummy site, which I'm going to change color, is now represented by a large polyhedral unit. So if we now go back to an expanded plot range, then we can represent this structure in terms of these very large polyhedral units. And that's a great way of understanding complex structures. You can actually define other sorts of frameworks and channels as well. Now, we've already met selection tools in CrystalMaker, and when we were looking at the spinel structure, we used a rectangular selection to isolate 2 layers of oxygen with the metal ions in between. You can use that technique to visualize crystal surfaces, but you can also slice away groups of atoms by showing a lattice plane in the crystal structure. And when you do that, you are able to start visualizing things like domain boundaries. Now, I want to just very quickly show you how we can compare 2 structures or 2 orientations in the same window. We're almost out of time, but this is just a very quick and quite an important thing to do. So let's just hide this. Let's hide this. And I'm going to find, have a look at silicon. And I have a silicon 111 surface here, which I created by using the selection tools. I could create another surface if I wanted to. I'm going to just duplicate this surface for a moment. So I've got 2 surfaces, and I'm going to take the atoms in this surface and I'm going to change their color. And then I'm going to make both of these structures visible. And we do that by holding the Shift key down while we click. Okay, well, we can't see anything because the 2 structures are on top of each other. I'm going to move one structure relative to the other one now. I'm going to take one of these structures and I'm going to lock it. And I'm going to use the move tool to move one relative to the other. And then I'm going to unlock. And now I can rotate. We now have an interface. Now, if I wanted to rotate, have an oriented interface, I could again lock one structure and then rotate one relative to the other, and then lock again. And now we can visualize our interface. We can do something similar by inserting a molecule into a structure. We can have 2 structures in the same document and we can make them both visible. We can actually merge multiple structures as well, and that's useful if you need to do simulations. I think the last thing that I want to show you is the fact that crystal structures don't have to be static. And of course, the properties of many materials are caused by their dynamical behavior. And CrystalMaker makes it very easy for you to visualize dynamical behavior by loading more than one structure in the same window and animating it. So let's have a look at animation very quickly. So I have here part of the crystal structure of SiO2 in its quartz polymorph. Those of you who don't have Apple Watches may well have traditional quartz watches on your wrist. Quartz is a very important material for its electrical properties and for the fact that it's pretty much everywhere on the surface of the Earth. But when you heat up quartz, it undergoes a structural phase transition involving tilting of the atoms, and we want to be able to visualize this. So I've loaded the crystal structure of quartz, measured at different temperatures, into the same document window. And when you heat the structure up, there are subtle changes, but not much happens. And I want to try and visualize that in more detail. So I'm going to take one of these structures. I'm going to switch to a polyhedral model. Let's just rotate it a little bit. I'm going to change the plot range slightly. Let's expand the Z range. And when I look down this axis, I can see a sort of a column layout. I'm going to use the lasso tool just to draw around part of the structure. And we're going to isolate a selection again. Oh, I didn't do very well there. Let's do that again. Isolate selection and hide the unit cell. And if we look at that from the side, we actually have a double helix of these blue tetrahedra. These are SiO4 groups. I'm going to select one helix. I can shift click on these atoms. We'll use the inspector to change the color of those to orange. And we can see it's a double helix. Now I want to be able to apply these changes to all the other structures in my list. And we can do that by going to the synchronize command. And CrystalMaker will analyze the visible structure and apply the changes that I've just made to all the other structures in the list. Now, if we use the play command, we can now animate those structures. So all we're doing is we're cycling through all of the structures in the document. And what's cool is that you can rotate whilst you animate. So we're looking at a visualization of the crystal structure of quartz with changing temperature. And you can see that as the temperatures change, these tetrahedra twist. And the effect of the twisting is to change the shape of this channel network from 3-fold symmetry to 6-fold symmetry. And in fact, there is a structural phase transition from trigonal to hexagonal. And we can switch to a ball and stick model and see that change as well, a space filling model, and so on. So animation can be a very useful tool for understanding changes, or for something as mundane as just looking at differences between structures, or by looking at the different frames from a simulation. So we use the lasso tool to isolate part of a structure. We colored part of the selection. We use the synchronize command and the play command. And I didn't say that we could actually export that as a movie. Okay, CrystalMaker does loads of other things as well. We have another hour which we can look at some more of the details. We can look at volumetric data. We can visualize things in 3D and so on. So I think we'll save that for the second part. Just maybe some tips for those of you who are getting started with the software. We strongly recommend that you do the self-guided tutorial that we provide on the help menu. It's not very exciting, but it does give you the essential nuts and bolts to get using the software. We do have some video tutorials on our website. If you have problems sleeping at night, that's a great way of knocking you out straight away. They're not the most scintillating of videos, but they are fairly comprehensive. There are some example files that we provide in the library. We have an online help, and we also have a user's guide available from the help menu, which is very comprehensive. So, and if you still have questions or if you have bugs, call us, support@crystalmaker.com. We're real people, and we're always happy to help. Call us, not Google. These are the video tutorials. A few quick tips. We do fix all known bugs. We have updates available from our website. You've seen the library. Be a bit skeptical of any files that you get from online databases. Many CIF files in particular are very fragile, and if edited, they can cause problems. We've seen how to automatically generate bonds and polyhedra. There are other things that you can use in the software to help you. I didn't mention that we do have multiple undo levels and redo levels. You've seen that the structures list allows you to make copies of the structure. You can use high resolution graphics, multi-touch, and we have video as well. I think I'll leave that for now because we are running out of time. In the second half, we can talk about more advanced features, including our diffraction software. So I'm going to switch out of the main screen. I'm glad to see some people are still there. That's excellent. Thank you for your patience. It's not the most enthralling watching somebody else operating a mouse and things. The way to learn really is to do this yourself. I'm very happy to answer questions, but if people wanted to take a break, we can maybe do the questions after the break. I mean, it's really up to other people. I don't know, is Afisa there?
I am, David. I think if we could have a 5-minute break,
yeah.
And then anyone with questions can come back after the break or drop it in the chat while we while we have a 5-minute.
That sounds great. And I also have some questions that were submitted ahead of time. So we have some answers to those, which I will be happy to share after the break, as they say. It's not a commercial break. So I'm going to go and have some coffee, and I will see you in about 5 minutes. So thanks for bearing with me. See you soon.